Hello, my name is Valerie Stolf and I will be reporting my results and observations for Physics 2212, Lab 4, Circuits and Capacitors. The purpose of this lab was to predict the behavior of circuits that contain resistors that are in series and also parallel to series, using the circuit construction kit, and to use multimeters to measure the values for the conventional current and the circuit's potential differences. The physics principles used in this lab are the conservation of energy and that the sum of the individual potential differences across a circuit sum to equal 0. The conservation of current principle that the overall charge of a circuit is conserved. Also used in this lab are Kirchhoff's loop rule, which allows the voltages across a circuit to add up to 0, and Ohm's law, which states that conventional current equals voltage divided by resistance. Overall, I found that the two ammeters in a circuit used to measure resistance were equal at a reading of 0.0204 amps, and that reversing the ammeter connection showed no change to the individual reading. For circuit 1, two 1.5-volt batteries were constructed on the left of the image, and two ammeters at 0.02 amps, calculated from Ohm's law, were constructed at the top and bottom of the circuit. When the circuit was tested with ammeters being installed reversed, the ammeter reading was still 0.02 amps. On the right, a 47 ohm resistor and 100 ohm resistor were constructed on the circuit. When the top ammeter was replaced with a voltmeter, the bottom ammeter then read 0 amps because the current could no longer flow through the circuit. The measurement recorded by the top voltmeter was found to be 3 volts. The circuit is now considered to be an open circuit since the voltmeter was in place of the first ammeter. To measure the potential differences throughout the circuit, the voltmeter was placed at the letter sections of the circuit to measure the voltage between segments. Between the two batteries from A to B, the voltage was found to be 3 volts. From C to D, between the 47 ohm resistor, the voltage was found to be negative 0.959 volts. From E to F, between the 100 ohm resistor, the potential difference was found to be negative 2.041 volts. Between all of the segments, the potential difference was found to be 0. When all the individual potential differences are added together, the sum was found to be 0, which matches predictions from the loop rule. The chart to the right graphs the potential difference throughout circuit locations. The difference increases as the current reaches the first battery and increases even more to 3 volts when it reaches the second battery. The difference begins to decrease as the current flows through the 47 ohm resistor, and then again as it reaches and flows through the 100 ohm resistor. This is not very realistic as it assumes an ideal voltmeter that has an infinite amount of resistance. I found that when the ammeter and resistors are arranged to be in parallel, the current increases to 0.06 amps. This is because current flows through the wire and the ammeter instead of the 100 ohm resistor, so more current is allowed through. Ohm's law was used to calculate the resistance at each part of the circuit. For the 47 ohm resistor, the resistance was found to be 47.95 ohms. The 100 ohm resistor was calculated at 102.05 ohms, and the resistance of the wire and ammeter were both at 0 ohms. This is because the wire and ammeter do not have any potential difference. Two RC circuits were built in this section, one with a charging capacitor and one with a discharging capacitor. With the charging capacitor, the light bulb dims as the capacitor becomes more and more charged until it is eventually not lit at all when the capacitor is fully charged. As the capacitor is fully charged, the current decreases. The charging time for the 10 ohm bulb was 21.2 seconds, and the charging time for the 20 ohm bulb was 43.3 seconds. For the discharging capacitor, the current is reversed and flows from the positive to the negative plate and decreases as the capacitor is discharged. The time to discharge for the 10 ohm bulb is 21.4 seconds and 42.5 seconds for the 20 ohm bulb. When the resistance of the bulb is doubled, the charging and discharging time is also approximately doubled. This was found using the voltmeter as the capacitor was charged from 0 volts to about negative 9 volts, and then discharging from negative 9 volts to 0 volts. The plot on the right shows a natural log versus time plot of the potential difference divided by the original potential difference, delta V naught. The graph shows that as the capacitor discharges, the voltage decreases linearly over time. The slope of the line is equal to negative 0.1664, which was used to find the value of RC and found to be about 6 seconds. This is the time it takes the potential difference to decrease to 1 divided by E of the original potential difference, which is the same as the ideal time constant at 6 seconds. To conclude, if a real ammeter was used in a real-life circuit instead of the online ideal construction kit, then the current reading would be lower than seen in this lab. This is because ideal ammeters have no internal resistance, so its voltage is very low and the current can pass through. In an actual ammeter, there is some amount of resistance that affects how much current can flow through the circuit. If a real ammeter was used, then the current reading would be lower than if the ammeter were not present at all. Furthermore, if a real battery and capacitor had been used, then there would be some resistance in these members, so the capacitor would charge slower as opposed to what occurred in this lab, where the members had no resistance and the capacitor was able to charge immediately. Thank you for watching.